So this is natural because basically electron chemical potential is the difference in chemical potentials between proton and neutron. So you have Un minus Up, which can be understood in terms of asymmetry. So this is also very clearly followed. Say for example, here at very high density, G1 and NL3 has a stiff symmetry energy. Correspondingly, the stiff chemical potential for G1 and NL3. So it follows the same pattern as the symmetry energy. So what is important here is that the point at which the K minus can come into the picture depends upon the density dependence of symmetry energy. So we have yet another importance for the symmetry energy that decides at what point the kaon will condense. So if you look into this picture, the solid dots here, they represent what could be the central density of neutron stars corresponding to these differentiation states. So now, if you compare between these two lines, so this dashed line which is for G1 and dotted line for G2, their equation of states are more or less similar, but the corresponding neutron stars, they have completely different central density. So this also can be explained, though the equation of states look very similar at the higher energy density, higher densities, they differ significantly at the lower density. The low density part is zoomed here. One can see that the equation of state of G1 and G2, they have different states. So due to this variation, so one can see the variation in the central density of the neutron star. Or in other hand, even small variations in the very low density part of the equation of state can affect the structural properties of neutron star. So it's not always true that you just worry about the very high densities. Even at the very low densities, there are some changes that will be reflected in the neutron star. Okay, so now once we introduce this antichaos, the equation of state changes quite drastically. So this is how it changes. So initially this NL3 was going like this. Now with these two antichaos, it becomes much softer. It becomes much softer than the density dependent interaction. So now one can say that the kaons play more role than the coupling constants itself. So these density dependent coupling constants are tuned so that the high density behavior is as desired, but becomes a bit softer. But we can achieve more softness by introducing these exotic particles like kaons. It's a similar case with this G2, G1 also. So G1 becomes much softer than IUFSC, though IUFSCs tend to be more softer than the rest. So these are the corresponding neutron star radius and mass relations for different interactions. So here there are few interesting points. So many of these calculations can, of course, explain the two solar mass neutron star. Of course, if you use either IUFSU or G1, then once the kaons are introduced, their mass becomes much lower. So with anti-kaons, these two models cannot explain the two solar mass neutron star. Another interesting point is that without anti-kaons, G2 and IUFSU, they give more or less the same neutron star with same maximum mass and same radius, corresponding radius. So there is a well-established correlation between the radius of the neutron star and symmetry energy. So they are supposed to be correlated strongly. But here we can see that this G2 and IUFSU, they suggest same maximum mass and same radius, though their symmetry energy is completely different. So here we see one exception for this rule, for this correlation. But of course, when you introduce this anti-kaon, the correlation is still weak. So similarly, one can introduce the lambda hyperon also, which comes actually ahead of K minus. So lambda hyperon also can change the equation of state significantly. This is the equation of state without lambda, or it's for a pure nucleon phase. This is how it changes when you introduce kaons. and this is how it changes when you introduce both lambda. So we can see that the introduction of lambda brings down the mass significantly, and the radius is slightly increased. Maybe I can summarize now. Even for a very soft equation of state, which are suggested by this higher order coupling, we find that there is a strong possibility of antichains to be condensed. The extended RMF models, which are quite successful in explaining several properties of finite nuclei, suggest a strong influence of higher order coupling as well as kaons in the neutron star, whose properties are well within the range of present observational constraints. The role of antichains is sensitive to the interplay between the density dependence of both symmetry energy and equation of state. So this is something very interesting. And without antichains and hyperons, many parameter sets could explain the two solar mass neutron stars. Whereas with antichains, either you require a soft equation of state or you require a soft symmetry energy. So the presence of exotic particles can increase or decrease the radius of the neutron star. So the sensitivity of the radius of such massive neutron stars maybe requires careful scrutiny whether we can infer something about the presence of exotic matter if we have accurate measurement of radius also for the maximum mass neutron stars.
Okay, so this closes the formal part of this conference. Now there would be, right immediately after this, a session where Thanksgiving and the highlights of this conference will be presented. So may I request Dr. Sushil Kumar, please, can you come on the dais? To give a summary of this conference. It's not a summary. It's just highlights of this meeting, which is again a personal thing. I have chosen it, the way I liked it. And so there were all the beautiful presentations, all the presentations were very nice, all the posters were very good. And I am really amazed that the quantity of work being done in this, in our country, and particularly in the northern India, which was once upon a time, nuclear physics was almost non-existent. But now it has been revived in a very, very big way all around over. Unfortunately, we are facing a drought from South India. Their nuclear physics activities have come down to kind of naught, because we don't have any representative coming from any South Indian university. I hope things will change there too, and next time when we meet, maybe there will be many more participants from that region of the world, whose work I may not have included in this highlights, because this is just a personal choice. And of course there is a rationale behind it, because I have picked up those things. We have many foreign guests here, our colleagues from abroad who have come all the way from various countries. So my theme has been that what we can learn from them, and in what way we can start a joint collaboration, if possible. So this has been my main theme. And also I wanted to highlight that some of the things that they are doing there, is it possible also to do that with our facilities? I picked up only those things which I feel that it should be possible to do these things in our country with our facilities. And so therefore a interaction with our colleagues from abroad would be very useful to us. So of course the greatest highlight of this conference was the beautiful cultural evening that we had, and I was even amazed to know that this whole thing was presented by the students of this campus. That's amazing, great, actually. They are no less than any professional whom you will pay a huge amount of money to bring them over and make them these presentations. This nice, this folk dance from Rajasthan, and to my foreign colleagues, I want to say that it is as romantic. You may not have understood the lines, but I tell you that those lines were as romantic. So I just wish that if we have that enthusiasm of a Bhangra dancer, that energy, then of course we can do lots of nuclear physics. Fine. So, the highlights. So first let me concentrate on nuclear structure physics. There was a beautiful presentation by David Jenkins, which I very strongly believe that this, whatever he is doing, can be repeated in our country. Should have been done in our country. So David shows that nuclei with N equal to Z above 56 nickel have several aspects which are very important for nuclear structure. For instance, NP pairing, starting from NP pairing to safe coexistence. These studies provide a test for the CBC hypothesis in fundamental physics. They are also of interest in astrophysics. So I wonder if we can somehow involve David in our facilities and try to do what he has been doing, because I could see that all those detectors, all those things that he is using in his experiment, we indeed have got those things in our country. So this would be a very, and this, if this can be done, then from Physical Research Laboratory, Ahmedabad. He talked about interacting boson model, various versions of it, and their applications to investigate exotic nuclear structure. He showed that this interacting boson model, although proposed in late 70s, but still continues to be very interesting. And one can study supersymmetry in nuclei, very important neutrinoless double beta decay, quantum phase transitions, structure of nuclei near proton and neutron triplines. So this interacting boson model continues to be of great importance, and in fact one of the early workers, a very pioneering worker in this field, is Olaf Scholten, who has now moved from this field to doing hadron physics. I am now collaborating with him, and whenever I meet him, he keeps telling me, "Oh, look, somebody from your country wants my code," which I wrote some 20 years ago, 30 years ago. The people are still interested in interacting boson model. I say, yeah, of course they are. There is a very active dynamic group in our country which they are interested in interacting boson model. There are experimentalists who are interested in interacting boson model, and so this area. This was, I think, one of the highlights of this conference. Then the poster session, amazing. There were some, approximately I counted 19, maybe even more posters on nuclear structure physics. They contained variety of techniques that has been used to study the structure of various nuclei, like projected cell model, cranked Hardy-Fock-Bogly-Bogue, relativistic mean field theory. So almost all the aspects of theory of nuclear structure physics is being pursued in this country. This is very heartening to know. I wished some of the, like for instance, there is a group which has put in 5 posters in this meeting. And this group, I wished a representative from that group would have presented a review of all the work that he has been doing. He is not too far away from here. He could have driven from Jammu, which is just very close by. He could have come here, and maybe he is busy with something or other. We should try to get him over. His group is doing tremendous amount of work. The next topic that I want to pick up is nuclear reaction studies with lighter systems. There were several talks on this subject, and also many posters. And the work also again has been done, many work has been done in our own country. So in this context, I have picked up the very beautiful presentation by Grigory Rogachev. He showed that resonance scattering with rare isotope beams provide direct access to continuum properties of exotic nuclei and can serve as a stringent test for theories like ab initio models, effective field theories, anti-symmetrized molecular dynamics approaches, and so on. So one of the things that I picked up, which appealed to me very much, because once upon a time I was also involved with that. That is to perform 7 beryllium-induced reaction on proton to populate the continuum states of 8 boron. And these continuum states of 8 boron has been calculated in ab initio theories and also in anti-symmetrized quantum molecular dynamics models, and they predict several states which could not be seen before. Now you have a possibility to see that. I wish the 7 beryllium beam, which was already developed by Inter-University Accelerator Center in Delhi in 2002, J.J. Das and my friend Madhavan, they were involved in that. And had we continued with that, and I just want to show what we achieved with that beam. That beam was there. Experiment was done. The first radioactive ion beam experiment in this country, and that remains the only experiment done in this country, with resources developed within the country, has been performed and has been published. You see, this is the result. This is the result. What was done was to study this transfer reaction, 7 beryllium and neutron, going to neutron and 8 boron. This reaction is of interest from the point of view of solar fusion process. Solar fusion reaction where one needs the cross section of proton plus 7 beryllium going to 8 boron plus gamma. This is solar fusion reaction. And it is very important to know precisely the astrophysical S factor for this reaction. And this was one indirect way, because this cross section for this reaction is required at very, very low energies, relative energies, and those energies are not accessible in laboratory. Although later on some people have performed some measurements for direct processes as well. But it is always better to have indirect measurements, and also, and so before that, these indirect measurements were always predicting a smaller astrophysical S factor than what direct measurements were telling. So this was for the first time that a direct measurement predicted a S factor which was very close to those obtained by a indirect measurement that we performed predicted a astrophysical S factor, which is in this range that is given here, to which was very close to those predicted by the direct methods, direct capture processes. Unfortunately, this beam was not continued. This program